In the last part, we have got introduced to grains and grain boundaries, and we have seen the grain boundaries are the region of mismatch between two grains which has two different orientations. And now let's look at why there is an increase in the strength when I decrease the grain size of my material. So there is an increase in the grain boundary fraction when I decrease the grain size. And let's look at the strengthening mechanisms, that is grain boundary strengthening in terms of grain boundary and its interactions with dislocations. So we know that when dislocations are not able to traverse through obstacles, such as let's say grain boundaries or second phase, they pile up on the slip planes at the barriers. What do I mean by that? So let's say here we have a grain boundary or let's say any obstacle, and this is a slip plane. So if these dislocations which are gliding on the slip plane, if they cannot further pass or cannot pass this obstacle, here it is a grain boundary, they will get stopped here and they will get piled up on the slip plane, and this piling up of dislocations create a back stress. Let us mark that also. So it can create a back stress here in this direction, or it can create a stress concentration on another grain or a neighboring grain. So this happens because of the pileup of dislocations on slip planes, or let's say at barriers. So here I have shown two TM micrographs. This is from our study and this is from a study by Schneider, and you can see that the dislocations are piling up on the slip planes across these boundaries, or they are stopped at these boundaries, and you can see that there is a piling of dislocations in this grain. Here also you can see that there is a piling of dislocations because they are being stopped at the boundaries. So these boundaries acts as a barrier for dislocation motion. So we have discussed this. Dislocations pile up against the barriers and they create a backstress, and thus they oppose the motion of dislocations which are gliding on this slip plane. And that is why the dislocations will be tightly packed near the head, that is at this boundary, and they create a backstress, and that is why these dislocations will be further spaced or widely spaced towards the source of dislocations. This is, let's say, there is a dislocation source here. So these dislocations here are widely spread, and these dislocations are tightly packed near the barrier. Here also you can see that here the dislocations are very tightly packed, and if I move away from the barrier, I can see that the dislocations are widely spread. And why is this? Because these dislocations will create a back stress on these dislocations which are gliding on this slip plane. Now we have seen that the grain boundary acts as a barrier for the dislocation motion, and it creates kind of a stress when dislocations accumulate or pile up at the boundaries. Now let's consider these two grains, and let's consider there is a boundary between these two grains. This red line is indicating a boundary between these two grains. And let's consider this slip plane. Let's consider this dislocation source which is at a distance of L from this grain boundary, and dislocation source, something like, you can say, we have talked about Frank-Reed source. So this kind of sources will be operating in the grain, and this dislocation source is at a distance of L from the grain boundary. Now let's consider we apply a shear stress and this dislocation source start operating. So let's consider the grain size, the average grain size of this material, or average grain diameter of the material will be D. And let's consider a dislocation which is generated here from the dislocation source, glide under the influence of this applied stress and comes across this grain boundary which is between grain 1 and grain 2, and it gets stopped at this grain boundary because there is a change in the orientation and this dislocation cannot further go. So it gets stopped here, and this dislocation source is keep operating, and you have dislocations which are generating which will glide on this slip plane and move towards the grain boundaries. And this happens, this continues, and you have a dislocation pile up on slip planes. So this dislocation pile up which is happening, you can see here that the dislocations here near the boundaries are tightly packed, but as I move towards the source, these are widely spaced. Why? Because these dislocations will create a back stress on these dislocations. Also, Let's consider this number of dislocations on the slip plane to be n. So these dislocations will create a stress concentrations or a stress concentration in a such a way that this dislocation pile up causes a stress concentration which can operate a dislocation source in the neighboring grain. So let's consider this tau c, which is a stress concentration or a stress or a critical shear stress to operate a dislocation source in the adjacent grain. So we have this grain 2 and you need a critical shear stress tau c which is needed to operate a dislocation source in grain 2. Now let's consider average resolved shear stress to be tau s and let's say a frictional stress tau I, that is when this dislocation glide on this slip plane, so there will be an inherent resistance which will be offered by the grain and that is called as a frictional stress, and this frictional stress can be equal to your tau p, and let me write that down also here. So this tau I can be equal to pulse Nabarro stress, that is a frictional stress offered by grain 1 in this case. And when we have this pile up of dislocations, the average resolved shear stress which will be developed in this grain, let's consider it to be tau s. Now what we write is that this tau c will be equal to n into tau s. So we have this n number of dislocations and the average resolved shear stress to be tau s. Thus tau c, that is a critical shear stress required to operate a dislocation source in the adjacent grain I can write it as n into tau s, and this tau s you can see that it will be tau a and subtracted by the frictional stress which is a resistance offered by this grain. So you can write tau s to be tau a minus tau I, and now let's see that shear strain and shear stresses, let's calculate that. So let's say one dislocation moves, it will cause a strain, that is a strain by B by L. So let's say we have traversing of one dislocation towards the grain boundary. Let's say it traverses L distance which has a Hall-Petch vector B. So the shear strain developed will be B upon L. That will be the shear strain developed by one dislocation. So if there are n number of dislocations, the shear strain developed will be n into B upon L. So you can write or find out a shear strain which is developed by n number of dislocations which are gliding on the slip plane. So let's consider each having the Hall-Petch vector B, and thus by one dislocation, if I move one dislocation from this point towards the grain boundary, there will be a strain which will be developed and that will be given as B upon L. And if there are n such dislocation, n number of such dislocation, that will be nb upon L. Now simply you can find out a shear stress by multiplying the shear strain by shear modulus G, and that is what you will get a shear stress here. Tau is equal to GNB upon L. Now you can find out what is n required or number of dislocations which are required to cause this tau c or to make this critical shear stress which will cause a dislocation source, which will operate a dislocation source in another grain. So this n you can find it out from this relation as n equal to tau s L upon GB. So let's consider this tau to be shear stress, average resolved shear stress, and you can find out what are the number of dislocations that are required. So you can say that tau c, I can find it out from this relation. Tau c is equal to, I just plug in this value of n in this relation and I get this relation as tau c is equal to LGB into tau s square. So we get this relation. Now you have tau s to be equal to tau a minus tau I, that is applied shear stress minus frictional shear stress. So we replace this average resolved shear stress with this term, that is tau a minus tau I. Let's do that. So here we replace tau s is equal to tau a minus tau I and we get this relation, and from there you can find out what is an applied shear stress. So you can say that applied shear stress tau A is equal to tau Y plus tau C Gp upon L to the power 1 by 2. And you can find out tau A. Now I bring this term L to the numerator and I can replace this tau C Gb to be as K dash, which is a constant here, and I can bring this L to be minus 1 by 2 here. So to L to the power minus 1 by 2. And what I can write here is that tau A is equal to tau Y K d to the power minus 1 by 2. So here I have replaced this L in terms of a grain size. So this is our grain size, and L was a distance from source, that is a dislocation source, to the grain boundary, and I can replace that L in terms of T, and I can make sufficient changes in the constant, and I replace this K dash with K, so it takes care of this relation. So we get tau A is equal to tau Y K d to the power minus 1 by 2, and this is what is a Hall-Petch relation. Let me write it down here. So this is what is our classic Hall-Petch relation, which relates the strength, increase in the strength because of decrease in the grain size. So here you can see that tau A is inversely proportional to under root of T. And this is the relation. This is a classic Hall-Petch relation which we have got. So here tau Y can represent a frictional stress offered by a grain. So you have this kind of scenario. You can say that there is a grain boundary here. Here you can see there is a grain boundary, and this dislocation accumulate at the boundaries, or this barrier creates a stress which can operate a dislocation source in another grain. And you can see this scenario here. So you have a dislocation source which gets operated in another grain. Now let's understand this relation. So we have larger grains, that means you have less number of grain boundaries, and thus the dislocations can glide easily to a longer distance. So this scenario will not have much of the barriers which are grain boundaries. But in case of finer grains, you have large fraction of these grain boundaries, and thus the dislocation experience a lot of barriers here in case of finer grains. So you have finer grains, you have more number of grain boundaries, more obstacles to the dislocation motion, and thus more strength. And this strength, increase in the strength, is quantified using Hall-Petch relation, which is given as tau A is equal to tau Y plus K d to the power minus 1 by 2. So this is an important relation which we have got, which tells that there is an increase in the strength of a material when I decrease the grain size of a material. Mind you, this is all valid for certain temperatures, that is equicohesive temperatures. So all this relation is valid till below equicohesive temperatures. Now let's move further and try to understand this relation. Now here we have replaced this tau A, that is as sigma y, and tau y as sigma star, which is nothing but a friction stress or a yield stress for infinitely large grain size, plus K upon under root of T. So where K is Hall-Petch coefficient, whose units are MPa meter to the power 1 by 2, and D is average grain size here, and sigma y is a flow stress of a polycrystal material. So here this Hall-Petch relation, if you see this relation, so this is the equation of line. So we can say that when I plot sigma versus d to the power minus 1 by 2, you can say we get a linear relation. And this intercept at this location where d to the power minus 1 by 2 is 0, you can say that this is a sigma star. That is, this will happen at infinitely large grain sizes. So this resistance offered by a grain of infinitely large size is called as sigma star. The slope of this relation is nothing but K, which is a Hall-Petch coefficient, and this has a significance in the deformation behavior. So we'll be looking at that also. So this is a Hall-Petch relation, that is a linear relation between sigma versus d to the power minus 1 by 2. I would like you to plot, let me write it down here. So for an exercise, you can plot this sigma versus d and see how this plot looks like. Here we have plotted sigma versus d to the power minus 1 by 2, but you plot sigma versus grain size, that is d. Now let's look at these two scenarios. Here you have sigma stars to be same, but k is changing. So this k depends on certain parameters, and let's say I have a different k in these cases. So here I have a smaller slope, here I have a larger slope. What does that mean? Let's say for the same grain size refinement, let me mark it over here, I can explain it. So let's say you have this initial grain size, let's say I call it as di, and I call it as d1 and I call it as d2. So here in this case you can see that the delta sigma will be much larger in this case, and in this case, so let me call it as sigma 2 delta sigma 1. So in this case where the slope is higher, there will be large increment in the stress by if I increase the or if I decrease the grain size. Here in this case where the slope is small, or if I decrease the grain size to d2, you have small increment in the stress. So if k is large, let me write that down also. So if k increases, delta sigma will increase, and that is what we can see from the slope. So here we are plotting sigma versus d to the power minus 1 by 2. If I mention a grain size over here, let me write that down also. So let's say if I put d values here, so here the d values will decrease. So that is a decrease in grain size here. Okay. So we have a decrease in grain size in this direction. Now we have seen importance of k. Now let's look at, so k indicates the dependency of strength enhancement on grain size. So you can say that more the k, there will be more strengthening which is happening by the refinement of grain size. That is what the meaning of this sentence is. Now let's look at the k remains same, but sigma star increases. That means you get more strengthening, inherent strengthening, and the sigma star indicates intrinsic resistance to the dislocation motion. So if I have more sigma star, I will have more strengthening. So if you want to increase the strength of a material, what you have to do is like you have to increase the intrinsic resistance of the strength, and you should have more or higher values of K. Now let's move on. And let's understand this Hall-Petch relation in terms of crystal structures and in terms of K and sigma. And here you can see that we have this classical Hall-Petch relation, and you have K and sigma for various materials. So sigma I here I have represented as sigma naught. So you can here write it as sigma I2. So you have sigma I and you have K, which is normalized using GB to the power 1 by 2. And you can see that for these three structures, that is BCC, FCC and HCP, so mean K value is higher for BCC compared with FCC. That means if I have higher values of K, you will get, if I refine the grain structure, you will have more strengthening. So in case of BCC, let me write it down here. So in case of BCC, we have K to be higher than, K of BCC is higher than K of FCC. So thus implies if I refine grain, delta sigma increase will be more in BCC as compared to delta sigma in FCC. This is what it means. So we have K for BCC structure to be more than K of FCC material. K is nothing but Hall-Petch coefficient. And if this is higher, that means the delta sigma, that is refinement in the strength or increase in the strength when I refine the grain size, will be more in case of BCC as compared to FCC. Similarly here in case of HCP, you have highest value of K as compared to FCC and BCC. Thus, if I decrease the grain size or refine the grain size, the increase in the strain will be enormous as compared to FCC and HCP materials. And here you can see that the intrinsic resistance which is being offered by the materials. So you can see here, let's say if I compare tungsten and iron, let's say both have BCC structure. Here, so we have BCC structure, we have BCC structure for iron. So you have more sigma I, that is intrinsic resistance, as compared to iron. So there will be a higher strength. This tungsten will possess a higher strength as compared to iron. So this is the importance of sigma I and K for different crystal structures. And let's move further. So let's understand the utility of this Hall-Petch relation. So we have seen this Hall-Petch relation. Let me write that down here. So we have sigma is equal to sigma I plus K d to the power minus 1 by 2. And here there are different materials which shows this or follows this Hall-Petch relation. So we have utility of this Hall-Petch relation is wide. So it can be applicable to different materials, different alloys, different metals. Also, one important thing is we can convert this strain to hardness by suitable conversion factors, and you can write this relation, that is an Hall-Petch relation, in terms of hardness as H is equal to H naught plus KH d to the power minus 1 by 2. So here this term will be varying, or these parameters are varying. So here the utility is, let's say you have stress and you have hardness. So in some cases, finding or measuring hardness is much easier as compared to measuring yield stress of a material. So the sample preparations are much easier in case of measuring hardness of a material. So you can use this relation to find out what is an effect of grain size on the mechanical behavior of material, just by correlating hardness or using this Hall-Petch relation for hardness. Now there is an important question. Is Hall-Petch relation valid for all grain sizes? So the answer is no, it's not valid. So we have this relation, and can this grain sizes take any sizes or any number? Let's say, can it go to nanometers to millimeters? So it is, can this take these ranges, or what is a limit on this grain size refinement? So let's understand this. So as I mentioned you, this Hall-Petch relation is not valid for all grain sizes. Now let's look at this in more detail. So here the first observations were made on grain sizes or materials with grain sizes which are much smaller or less than 50 nanometers. You can see here the grain size is decreasing here. So here the grain size is 16 nanometers, it is 6.25 nanometers. So this was first observed by Professor Atul Choksi, who is now professor at Indian Institute of Sciences, Bangalore, and he first observed in copper, nanocrystalline copper and palladium, that when I decrease the grain size, the strength decreases, or here he has plotted hardness. So they have shown that the hardness decreases with decrease in grain size, which is against of this relation. So this relation, what it tells, when I decrease the grain size, the strength should increase. But what they have observed, Choksi and his co-workers, they found that there is a decrease in the hardness with decrease in the grain size. So if I'm going to decrease my grain size, the strength is also decreasing. And there is a compilation of data which shows that if I reach to certain grain size, let's say if I decrease grain size beyond certain size, the strength actually drops or saturates. It doesn't increase, or it doesn't follow this Hall-Petch relation. This is also mentioned over here. So if I decrease the grain size, I will start decreasing the strength. So here, from here you can say that if I'm decreasing the grain size, it increases the strength, but as soon as it reaches to certain value, now if I start decreasing the grain size beyond this value, the strength start decreasing, and there is a negative slope. So K becomes negative here. That is decrease in strength with decrease in grain size. So Hall-Petch is not a universal law. Hall-Petch is valid for a limited range of grain sizes. Now let's look at this observation, and this observation is termed as inverse Hall-Petch relation. So we have this Hall-Petch relation. We can see that when I decrease the grain size, there is an increase in the strength, which follows this classic Hall-Petch relation, and after certain grain size, the strength drops or decreases. So we have to find out why the strength is dropping over here. We have seen in this region that grain boundaries acts as an obstacle, and thus they increase the strength. So if I decrease the grain size, there will be more number of grain boundaries and there will be more obstacles to the dislocations, and thus the strength is increasing. And we have seen this, or we have proved it with a mathematical model. Also here, now what is happening? So here in this case, let's understand what is happening if I decrease the grain size, why the strength drops. So Choksi et al., they reasoned that there is a Coble creep in nanograins at high stresses. So we'll be understanding what is the Coble creep. So let's say if I decrease a grain size beyond certain value, so there will be more fraction of atoms which are at the grain boundaries. So if I decrease the grain size, volume fraction of atoms residing at grain boundaries and triple points. So these are triple points where three grains meet. So we have grain boundaries and triple points or triple junctions. Their volume fraction increases, or the atoms residing at these boundaries, the volume fraction of atoms residing at these boundaries and triple junctions will increase. And these boundaries now act as a pathway for a diffusion, and that is what happens. So you have a creep, that is a diffusion of atoms along these boundaries, and that happens at higher stresses. So we'll be looking at this when we discuss about creep, but here the point is, if you decrease the grain size, the grain boundary fractions increases and the atoms residing at these boundaries also starts increasing, and beyond a critical value at higher stresses, this grain boundaries where the bonds are broken, there will be a diffusion happening along these grain boundaries, and that causes to drop in the strength of a material. So when I talk about grain boundaries here, we can see that there are grain boundaries, there are triple junctions, and there are grain core. And here you can see that I have plotted volume fraction versus grain size. So as I decrease the grain size, what happens? The triple junctions increases or grain boundary fraction increases. And in other words, we can say that the interfaces are increases, and this increase is drastic when I decrease grain sizes to certain lower values. So interfaces are nothing but comprising of grain boundaries plus triple junctions. And thus you can say that when I decrease the grain size beyond certain value, the interface increases, atoms residing at these boundaries increases, and they can diffuse at higher stresses along these grain boundaries. And thus there is a decrease in strength. And this kind of phenomena is called as inverse Hall-Petch. Now let's look at let's revise what is an effect of decrease in grain size on yield stress in terms of Hall-Petch and inverse Hall-Petch. So you have Hall-Petch phenomena occurring here. So that is, if I go on decreasing the grain size, then there is an increase in the strength. In this region, you get grain boundary sliding, and in this region, you have an inverse Hall-Petch. So here in this case, what you can say that the grain boundaries are stronger than the grain interior. In this region, the grain boundaries are weaker than the grain interior. Now let me explain it to you. So let me explain it to you here itself. So let's say you have grains here and you have another grain here. So let's say this is grain 1 and grain 2 and this is a boundary over here. So this boundary, if I go on decreasing the grain sizes, this boundary will act as a pathway for diffusion, and thus the strength of this grain boundary will decrease if I go on decreasing the grain size, and thus you see this manifestation of Hall-Petch or inverse Hall-Petch. Now let's look at what is a minimum grain size that you may need. Okay. So you have a criteria, we have seen the dislocation loops. So at least one dislocation loop must fit into an average grain. So let's say you have material like this, and let's consider this as a dislocation loop. So minimum diameter of dislocation loop, let's consider it as D here. And here you have 3 dislocation loops. So what can be the minimum grain size that you can achieve to have more strength in a material? So that limit is theoretically given as at least a 1 dislocation loop should be there inside that grain. So this D is equal to the grain size of my material. So if I reach this grain size, I can still retain the strength, but if I go on decreasing the grain size beyond this D value, there will be a decrease in the strength. So here, let me write it here. So you can get strength, you can improve strength till D, that is a diameter of this dislocation loop. If I decrease grain size beyond this D, so let's say D1 is less than this D, I will see that in such kind of grain sizes, I will have an inverse Hall-Petch, that is a decrease in the strength with decrease in the grain size. So you can write in other words the interaction of characteristic length, that is a dislocation loop diameter, and a size parameter, that is we can correlate this dislocation loop diameter with respect to our grain size. Now there is one more important thing which I would like to point, is that if I go on decreasing the grain size, there is a grain growth even at room temperature. So let me explain it to you. I have explained it that grain boundaries, if I decrease, they can be a pathway for diffusion. So if I decrease the grain boundaries, they can act as a pathway for diffusion when you apply stresses. And thus here there is a studies which have shown on copper. You can say that this copper was synthesized and they were kept in a ambient temperature for certain long days, and you can see that there is an increase in the grain size even at room temperature. So this nanograined material show grain growth even at room temperature, and thus the microstructure may not be stable. So you have to be very careful when you want to synthesize material in nano sizes. The grain sizes are in nano, you can tend to see a grain growth even at room temperature.